Good morning, good afternoon, good evening. Guys, today we are starting chapter 9 and 10. Notice I said 9 and 10, and that's because I have taken these two chapters and I've kind of blended them together, and I do them as one topic on energy. Okay? So that you know what I'm doing. I'm doing a combined kind of 9-10 chapter. Now, in these two chapters, we're going to explore energy. The concept's been around since the late 1800s. Okay? Energy is one of those slippery topics in that I can show you a baseball. I can show you matter. I can't hold energy in my hand per se and say, look at the pretty energy. Okay? We see energy in its effects. So when we talk about energy, we can call energy natural money. It's the ability to do work. It's the ability to apply and force and make something start moving that was sitting still, or take something that's moving and stop it, or in some way change its speed. Key word there is speed. Okay, I can speed it up, make it go faster. I can slow it down, make it go slower. Now, energy comes in two main categories. There are subcategories inside these categories, but two main categories. We talk about potential energy and kinetic energy. There are different kinds of potential energy, there's different kinds of kinetic energy, and we're going to start our exploration of energy looking at macro scale forms of potential and kinetic energy. Macro, remember, is up here in the world of the big. An ant, in the grand scheme of things, is considered macro. If we can see it with our eyes, macro. Okay? Unaided eyes. If it can be seen with a microscope, it's microscopic. If it's so small I can't see it with a microscope, it's submicroscopic. Next semester, we'll concentrate in a lot on submicroscopic forms of potential and kinetic energy. At first glance, we can say that kinetic energy is energy something possesses because it's moving. And potential energy is stored energy associated with an object's position or the arrangement of particles. Thermal energy, which is going to be a big topic next semester, okay, is the sum of microscopic kinetic energies and vibrational potential energies of atoms and molecules. We'll mention thermal energy just a little bit this semester. Okay? Now, as we study energy, we're going to talk about system and environment, or system and surroundings. Okay? So we're going to look at interactions between the system and the environment. And why did I put that in there twice? Interactions between the system and the environment, and interactions with this, within the system. Okay, I got to pay attention to what I write. So let's define system and environment, or surroundings. The system is some small piece of the universe that we're interested in. So we're interested in the motion of a specific object, or a specific group of objects. There's something we're studying. The environment is everything external to the system. So I might call a baseball interacting with the Earth's gravitational field a system. And a puppy dog walking down the street would be part of the environment. Okay? So if you're not in the system, you are in the environment. Sorry guys, I hit the wrong button. Now, some symbols we're going to use. E, we're going to use for energy. ESYS is the total energy of the system, and EENV is the total energy in the environment. Capital K is going to be used for kinetic energy, a capital U for potential energy, and if you see an E with a TH subscript, that's thermal energy. We can also talk about chemical energy and electrical potential energy, and we can talk about radiant energy. There's all kinds of things, but for right now, we're going to stick with kinetic energy, potential energy, thermal energy, total energy of the system, total energy of the environment. Okay? As we're looking at energy, we're going to talk about transformations and transfers. Within a system, we're going to talk about transformations. It's the change from one form of energy to another inside the system. So nothing's leaving the system, nothing's entering the system. So the total energy content of the system doesn't change. And we're going to talk about transfers of energy. That's when energy moves between the system and the environment. Now that's going to be very important next semester when we talk about thermodynamics. This semester we'll just kind of touch on it a little. When we transfer energy to or from the system, we're going to change the total energy content of the system. And when we talk about moving energy in and out of the system, we're going to talk about work, and we're going to talk about heat. Now, when we talk about work can be involved in transfers in and out of a system, and it also can be part of transformations of energy inside a system. But no matter whether we're looking at a transfer or transformation, the symbol for work is a W. Heat is the transfer of energy by way of submicroscopic interactions, which means that the thermal process, and the symbol for heat is Q. Q is going to be important, really important, next semester. Okay? Now, let's look at this diagram. Inside the system, we have transformations. So I could take kinetic energy and change it to potential, potential change it to kinetic, kinetic could go to thermal, thermal could go to kinetic, thermal could go to chemical, chemical could go to thermal, chemical could go to potential, potential. Chemical is a kind of potential energy, so you could talk about changing kinds of potential energy. We can crisscross all over the place in there, okay? Those are transformations inside the system. Transfers are either energy coming in to the system from the environment or going out from the system to the environment. Okay? So, heat we'll eventually get to. If the system is not interacting with the environment, then we can say that there are only transformations, no transfers, and the energy inside the system doesn't change, so the change in energy of the system is 0. Okay? If the system is interacting with the environment, the change in energy of the system won't be 0. Now, right now, we're going to deal with work as a way to move energy out of the system, in and out of the system, or we're going to work as transformations. We're going to concentrate in on transformations inside the system first, then we'll move on to transfers. Now, keep in the back of your head, we'll come back to this later, that any change in energy inside the system, we're going to look at right now as due to an external work. So if you see work EXT, that means that it's work done by something external to the system. Okay? If the work external is positive, we're adding energy to the system. If it's negative, we're taking energy away from the system. Makes sense. If we have a positive change in energy of the system, delta E, we've added energy in. If it's negative, we've taken energy away. Okay? Now, what we're heading toward here is a basic energy model. Okay? And this is an image very similar to the one that we were looking at earlier. This one says we're only looking at situations where external work is done on or by the system and no heat is moving in and out of the system. So work in, work out transformations inside the system. Okay? Now, if we have an isolated system, one that's not interacting with the environment, there's no work being done by the system or on the system, and all we see are transformations inside the system. So, simplifying it down as much as possible, kinetic could go to potential, potential could go to kinetic inside the system, kinetic energy could go to thermal inside the system, potential energy could go to thermal inside the system. Notice that these are one-way arrows. Okay? That's important. Now, let's start by looking at macro scale kinetic and potential energies. Okay? Now I'm going to throw a new term at you, mechanical energy. Mechanical energy is macro scale forms of energy. Okay? So E mechanical is going to be the grand sum total of the macro scale energies inside our system. Kinetic energy, like I said earlier, is energy something possesses because it is moving. So if we look at a single object that's experiencing a constant force, okay, then we can say the following. Now, the book goes through the whole derivation of this, but I'm not going to go through the derivation. We're just going to cut to the chase. Okay? Kinetic energy here equals 1/2 mv squared. So kinetic energy, you can see, depends on velocity, or speed would be a better thing for me to say here. Notice that velocity is squared. Since velocity is squared, that means K, kinetic energy, is always going to be a positive value. Kinetic energy can never be negative. Okay? Now, if I look at the units for K, kinetic energy, I have kilograms times meters squared over seconds squared, which is a joule, okay? Which we call a joule. It's a combined unit. A joule is also is equal to 1 Newton meter. So our units of energy is going to be the joule. And a joule is the same as a kilogram meter squared over second squared, or a Newton meter. So let's look at a really simple question. What is the kinetic energy of a 250 kilogram go-kart traveling at 15 meters per second? Well, we know that kinetic energy equals 1/2 mv squared. So it's going to be 1/2 times the mass, which was 250 kilograms, and it's traveling at 15 meters per second squared. So 250 times 15 squared divided by 2 gives me 2.81 times 10 to the 4 joules of energy. Okay, that's not hard. So let's move on. Let's say, how fast would an 80 kilogram person on a bike, so let's say the person and the bike together is 80 kilograms, have to travel to have the same kinetic energy? Well, 2.81 times 10 to the 4 joules would have to equal 1/2 times 80 kilograms v squared. So I multiply through by 2, divide by 80, and then take the square root. The velocity here would be 26.5 meters per second. And that's the speed. Notice it's not got the arrow over the top of it. So the person, to have the same kinetic energy, the person on the bike would have to move faster. Okay? Now, let's think about change in kinetic energy. So if kinetic energy changes, there has to be an applied force, because we know to change speed, there has to be an acceleration. And accelerations are based on forces. So one of the things we know is that to change the kinetic energy, we're going to have to do work on an object. So work is equal to change in kinetic energy, which is K final minus K initial. Work is related to force being applied, and therefore we can say work is equal to the integral of S initial, S final, F ds. Now, right now, we're working with constant forces. So we can say that work is equal to the force along the direction of movement, delta S. Now, let me draw you a picture here. Here's our S initial, and here's our position S final. S is just any arbitrary axis. So there's our delta S. Okay? If I have a force here, F, then only this portion of the force, F sub S, is going to change the speed of the object. This portion, F perpendicular, isn't going to do anything to the speed of my object. Remember, perpendicular forces would try to change the direction that an object is traveling. Now, there could be some other forces in here that balance out that force so that there's no motion vertically the way that I've drawn it, but only the portion of the force parallel to the direction of travel does any work. Okay? So for a constant force, work is equal to F sub S delta S. And work equals change in kinetic energy, which is 1/2 m V final squared minus V initial squared. Okay, so both of those things are related. So let's drop a 1 kilogram ball from a height of 2 meters and think about how much work gravity is doing. Okay, now if I have a ball here, it's experiencing a downward force F sub g. So if it starts up here at y equals 2 meters, and I go to a y final equals 0 meters, okay, and it has a mass of 2 kilograms, then our force due to gravity, is going to be 2.00 kilograms times 9.8 meters per second squared, so that's 19.6 newtons. Okay? Now if we think about directionality, our force is down, our direction is down. So if I look at this, my work is going to be my force minus 19.6 newtons times my delta y, which is 0 minus 2 meters. So I have 19.6 times 2. The negatives cancel out. I get 39.2 joules worth of work done. Okay? Now, if I say that velocity initially for the ball was 0, I can say 39.2 joules is equal to 1/2 times the mass, 2 kilograms, V final squared minus V initial squared. So I have 39.2 joules is equal to 1 kilogram V final squared because V initial was 0. So I get V final to be 6.27 meters per second. Now, that's a speed, not a velocity. It's very easy for us to say, well, that ball has to be going down, and I can change that speed to a velocity fairly easily, but, you know, we gave up a little bit of information for a slightly easier approach. Okay, Skater, go way up. Go on up. Now, besides kinetic energy, for our system on large scale, we can have potential energy. Energy that's stored. A better definition is energy due to position or arrangement. Now, there's several types of potential energy, and they all are associated with what we call conservative forces. And forces at a distance are conservative forces, and spring forces are conservative forces. So we're going to start out initially with gravitational potential energy. Then we're going to talk about spring potential energy. Okay? Now, gravitational potential energy is always given the symbol U sub G. It's energy something has because of its position above the Earth. Okay? UG is always equal to mgy. Now, gravitational potential energy can have a positive value or a negative value, all depending on where you set your y equals 0. The important thing to remember about potential energy, and especially about gravitational potential energy, is we're always really more interested in change in potential energy instead of the absolute potential energy at a point in space. Because the absolute potential energy, again, depends on where you set your y equals to 0 to be. So let's look at we're going to look at some transfers and transformations of energy, and when we do that, we're always looking at changes. Okay? So potential energy is associated with conservative forces. I said that before. A conservative force is defined as a force for which the work done is independent of pathway taken. So if I take this box, okay, and I move it from here to here, I have a specific change in height, I have a specific change in gravitational potential energy. If instead of coming straight down, I go over, back, over, back, over, back, and down to the same height, I still have the same change in gravitational potential energy, even though I took a new path to get there. Okay? So it doesn't matter how I go from point A to point B, only that I went from point A to point B to look at the change in gravitational potential energy. Okay, so a 1 kilogram box at a height of 6 meters above the ground would have a gravitational potential energy of what, assuming that y at the ground is 0? Well, UG equals mgy, so it was a 1 kilogram box, and G is 9.80 meters per second squared, and our height was 6 meters. So 9.80 times 6 times 1, I get 58.8 joules. That would be its absolute potential energy. Okay? Now, this is when y equals 0 at ground. What if I now took that same object and I was hanging it over a hole that was 2 meters deep? So I put my y equals 0 at the bottom of the hole. So now the ground is y equals 2 meters, and our object is up here at y equals 8 meters. UG now would be 1 kilogram times 9.80 meters per second squared times 8 meters. Okay, so 8 times 9.80 would equal 78.4 meters. Joules. Okay, see how the absolute gravitational potential energy looks very different from the two places? But if I looked at change in gravitational potential energy from this height to the ground, for case 1, I would have 0 minus 58.2 joules, which would be a minus 58.2 joules. For our case 2, I would have a gravitational potential energy now that it's not 0. I would have a 1 kilogram times 9.80 meters per second squared times 2 meters minus the 78.4 joules, and I would get a minus 58, that's 58.8. 58.8 joules again. So the important takeaway here is that the absolute value of gravitational potential energy is not what's important, but change in gravitational potential energy is what's important. Okay? Now, other thing to point out here is if I took that object and I slid it down a frictionless ramp instead of dropping it straight down, the same change in gravitational potential energy would happen. When we combine gravitational potential energy and kinetic energy, we get mechanical energy. So E mechanical equals K plus U. Now, this brings us to the law of conservation of energy. It's essentially the first law of thermodynamics. It says that energy cannot be created or destroyed. It can only be transferred or transformed. This means that the grand sum of energy of the universe should be constant. Any energy lost by a system should be gained by the surroundings. Any energy lost by the surroundings should be gained by the system. For an isolated system, one that's not interacting with the environment, the total energy inside the system would be constant. So this would mean that the mechanical energy of the system would be conserved. Okay? As long, there's a caveat here, as long as we are dealing with only conservative forces. Okay? The main thing, okay, for an isolated system, the energy inside the system isn't going to change. We go one step further, we say if the only forces at work inside the system are conservative forces, then mechanical energy is conserved. So we're going to start looking at systems where we have conservation of mechanical energy, where we only have conservative forces. Okay? So the total mechanical energy must be equal before and after if we have only conservative forces. This refers back to law of conservation of energy, and we've now gone a step further and we've got the law of conservation of mechanical energy, which says that the total mechanical energy for a system where only conservative forces are at play is constant. So E mechanical initially has to equal E mechanical finally. So for systems where we have only conservative forces, change in mechanical energy is 0. So kinetic energy initially plus gravitational potential energy initially has kinetic final plus gravitational final. If we start playing with it, just doing a little algebra, scroll up, we can get down to the fact that if I look at the change in gravitational potential energy and kinetic potential energy, the negative of the change in gravitational potential energy equals the change in kinetic energy. Okay? So I have potential energy being converted into kinetic energy, or kinetic energy being converted into potential energy, and whatever change we see in potential, we see the opposite change in kinetic. So if potential energy goes down, kinetic energy goes up. If potential energy goes up, kinetic energy has to go down. So if we drop a ball, okay, and we're under the influence of gravity and gravity only, no friction, okay, we can see that the gravitational potential energy that the ball had to begin with is going to be slowly converted into mechanical energy as the ball drops. By the same token, if I throw a ball up, it's going to start out with kinetic energy, and as it goes up, the kinetic energy is going to be transformed into potential energy, okay? But the grand sum total of energy is going to be the same. By the way, guys, we could use this with projectile motion. If we say that it had so much energy when it was launched, then we could calculate how high it's going to do based on gravitational potential energy, okay? So let's move on and let's look at some problems. So we're going to look at problem 5 at the end of chapter 9, okay? We're going to be on page 227. Get over here to 227. Get down here to the problems. Okay, if we look at problem 227, problem 5 on page 227, it says a 25 kilogram box sliding to the right, to the left across a horizontal surface is brought to a halt in a distance of 35 centimeters by a horizontal rope pulling to the right at 15 newtons of tension. How much work is done by tension and how much work is done by gravity? Well, number one, the box is not moving up and down any. If it's not moving up and down any, there's no work by gravity. So the answer to B is 0. We don't have to do anything there. Okay? But we do have to worry about the tension. So let's worry about the tension. So let's look at the situation that we've got here. Okay, we've got a box here, and it's moving initially. The initial is in this direction. I'll call this x initial equals 0. It's got a tension force on it in this direction, and our x final is 2 meters. Okay, so the work done by the tension is F delta X. So the force here is 15 newtons, and our delta X is minus 2 meters minus 0. So I get a minus 30 joules. I'm reading the right, oh, excuse me. I read the wrong line. I got to pay attention. It's a minus 0.35 meters. So minus 0.35 meters minus 0. And I get my work here to be a minus 5.25 joules. Now, that means that I'm taking energy away, okay? So work also equals change in kinetic energy. So the minus 5.25 joules has to equal 1/2 mv final squared minus 1/2 mv initial squared. And we are told that out at this point, v final equals 0. So I might have a minus 5.25 joules equals 1/2 times the mass, which was given to us as 25 kilograms, times 0 squared, minus 1/2 times 25 kilograms V initial squared. So if I solve for V initial, I am going to get 5.25 times 2 divided by 25, take the square root, 0.648 meters per second. Now, that is a speed. The problem only asks us to find the work done by the rope, but I went ahead and got the speed because I'm wanting to remind you guys that any work that we do is going to cause a change in kinetic energy. Okay, now let's look at problem 6. Same page. Okay, problem 6 says a 2 kilogram book is lying on a 0.75 meter high table. You pick it up and place it on a shelf 2.25 meters above the floor. How much work does gravity do on the book, and how much work does your hand do on the book? Now, if you think about this, your hand is working upward, gravity is working downward, okay? And the book doesn't end up with a velocity at the end, so all the work that you put in with your hand actually goes to changing the gravitational potential energy. So there's a couple of ways that we can look at this, okay? Force due to gravity is equal to mg in magnitude. So the mass is 2 kilograms, 9.80 meters per second squared. So our force due to gravity is 19.6 newtons, okay? The work done by gravity is going to be force due to gravity times delta y. Now, if you start out at a table height y equals 0.75 meters, and you go up to a height of y equals 2.25 meters, then our change in y is going to be, and I didn't write it out, I punched it all. So 2.25 minus 0.75, 1.50. Okay? So work done by gravity is the force due to gravity. Direction-wise, it's 19.6 newtons, because if you think about this book being lifted, force due to gravity is pointing down, force from the hand is going up. So I have 19.6 newtons times 1.5 meters. So the work here done by gravity is a minus 29.4 joules. Okay? Now, if I'm lifting that book up at a steady, pace, the work done by the hand, okay, would equal the force from the hand times delta y. And the force from the hand is going to be identical to the force due to gravity, just pointing in the opposite direction. So it's plus 19.6 newtons. And delta Y is 1.5 meters. You get a plus 29.4 joules. So the work your hand is doing is being directly opposed by gravity, okay? And what's happening here is the energy you're putting in to try to accelerate it is essentially going to end up in gravitational potential energy. Okay? Now, I also have on my list to do problem number 9. I've got it worked out in the problem sheets I'm giving you. I'm going to let you do that one on your own and check it against what I've done and given you. Okay? So, let's move on. Motion under the influence of gravity is not the only situation where we encounter a conservative force. The next conservative force on our hit list is a spring force. A spring force is called a restorative force because when you take a spring of a certain length and you either pull it out or you push it in, the spring pushes back in the opposite direction. So if I pull on the spring wants to pull back. If I push or compress the spring wants to push out. And it's a restorative force. The spring always wants to go back to its natural length, which is called its equilibrium position. Okay? So whether I stretch or I compress, it wants to go back to its original length. Force from a spring is always equal to K delta S, where delta S is the change in the length of the spring. Okay? Think about delta S there being in absolute values too. I should have put it in there, but that's okay. So the further you displace a spring, the harder it pushes or pulls. So hint, okay? A spring force is a variable force. That's going to pop up later, but for right now, okay, a spring force depends on how much it's stretched or compressed. So we can determine the K value, the spring constant for a spring, by hanging masses from a spring and allowing the system to come to a new equilibrium position. Okay? So we can say the force of a spring plus force due to gravity is equal to K delta S plus a minus mg. So we get K delta S to be mg, or we can say K is mg over delta S. So we're going to look at problem 27 on page 228. Do a really simple calculation of K. There. So it says a 10 centimeter long spring is attached to the ceiling. When a 2 kilogram mass is hung from it, the spring stretches to a length of 15 centimeters. What is the spring constant? So in this problem, we're trying to find K, the spring constant. Okay? Now, what we're given is that the change in the spring length is going to be 15 centimeters minus 10 centimeters, which is 5 centimeters, which is 0.50 meters. Okay, and we're told that the mass that we hung on this was a 2 kilogram mass. So K, the spring constant, is going to be 2.00 kilograms times 9.80 meters per second squared over 0.50 meters. So 2 times 9.8 divided by 0.5 says that our spring constant is 39.2 and it's Newton over meters. A kilogram meter over second squared is a Newton, so I have a Newton per meter. Okay, so Newton per meter. Not a hard problem. All right, now, let's think about the direction of the spring force. Okay, if I stretch, let's draw a picture here. I'm going to attach a spring to a wall. Okay, here's its natural length. So this is considered x equals 0. If I take that spring and I now stretch it to right here, I have something attached to the spring. Okay, there's our x equals 0 position. The spring is going to want to pull that direction because I pulled it out. And if I were to compress the spring back to here, notice where it is compared to x equals 0. The force now from the spring points in that direction. So if I displace to the right, the force is to the left. I displace to the left, the force is in the right. The spring force always points in the opposite direction of the displacement. So when we're dealing with springs, we make our coordinate system so that the 0 position, if I'm laying it flat, horizontally, the x equals 0 position is going to be the natural length of the spring. And to the right, pulling it out, stretching it would be positive, and moving it to the left would be compression, that would be negative. So we talk about a spring force being equal to minus kx, where x represents the displacement from our equilibrium position, where equilibrium position is x equals 0. So let's look at problem 28 on page 228. Okay, problem 28. Now, it says a 60 kilogram student is standing atop a spring in an elevator as it accelerates upward at 3 meters per second squared. The spring constant is 2,500 newtons per meter. How much is the spring compressed? Now guys, there is another problem hidden in here, okay? Namely, that student is standing on a spring that is accelerating. So I've got to calculate essentially what the force that the spring has to apply based on the fact that my system is accelerating. All right, so they pulled a sneaky on you, so be careful here. All right. So if we think about the person standing on the spring, okay? Whee, my person standing on the spring. They're sitting on that and they're on a spring, okay? Then if we look at the sum of the forces on the person, we've got the force from the spring plus force due to gravity has to equal mass times acceleration. So the force of the spring, force due to gravity would equal mg, and the mass of this person is given as 60 kilograms times 9.80 meters per second squared, so that our force due to gravity is 588 newtons. Okay, so the force due to the spring minus 588 newtons has to equal the 60 kilograms times the acceleration, which is a plus 3 meters per second squared, because up is positive here. So that force from the spring would equal I calculated it. Force from the spring is 768 newtons. Now, if I think about this, you know, as my y equals 0 position, we're now at a y final position. The spring started out like this, and now the spring is compressed. Okay? The force from the spring is in the positive direction. My spring is compressed. Force from the spring is equal to minus ky in this case. So I have 768 newtons equals a negative, and the spring constant was given to us as 2,500 newtons per meter times y final, or I'll just say y. So if I calculate for y is going to equal a minus 0.307 meters. That negative sign indicates that it was compressed. Okay? So that's how much the spring was compressed while this person was standing on it, accelerating upward. I like this problem because it gets you guys to think about the fact that we had to do something to figure out the spring force to get started. Okay? All right. Now, let's talk about spring potential energy. Every time I stretch or compress a spring, I store energy in that spring because the spring wants to move back to its initial equilibrium position. So it turns out that spring potential energy is equal to 1/2 K delta S squared, or if I'm moving along the X position and I have X equals 0 being our equilibrium position, I can say spring potential energy equals 1/2 K X squared. I want you to notice here, since X is squared, it doesn't matter if it's compressed or if it's stretched, I'm always going to have a positive spring potential energy. Okay? I can have a negative change in spring potential energy, but I'm never going to have a negative spring potential energy. So let's look at problem 15 on page 256. Now guys, I'm making a leap over into chapter 10. Okay, because remember I told you when I started this, I'm kind of blending chapter 10 and 9 together. So let's look at problem 15 here in chapter 10, section 3. It says, how far must you stretch a spring of 1,000 newtons per meter K to store 200 joules? So let's store 200 joules. So U spring is equal to 1/2 K X squared. And we know that we want to store 200 joules. And the spring constant here is 1,000 newtons per meter, X squared. So 200 times 2 divided by 1,000, I get 0.400, and that will be meters squared is equal to X squared, and I take the square root, and I get X to be 0.632 meters. So I can stretch the spring 0.632 meters, or I could compress the spring 0.632 meters, and I would end up storing 200 joules. All right? So, if I have a mass spring system where the spring is either attached to one side of a mass or it's sitting against a mass, okay? So if you think about it, if I had a mass there and it's just sitting against the spring. What we can say if we're on a flat surface is the kinetic energy initially plus the spring potential energy initially has to equal kinetic final plus spring final. We could go through the same thing and say that any change in spring potential energy equals an opposite change in the kinetic energy of the system, but I kind of like using it in this form. So let's think about a mass spring system and where the kinetic energy is the greatest. So let me draw a picture for you, okay? If I think about having a spring here, and it's attached to a box, okay, and this is our x equals 0 position. Lock your doors, okay? Yeah, I'll be down there and just finish this up. If I start out here at an x equals initial position out here, okay? And at this point, V initial equals 0. As I let this go, it's going to start moving in this direction. The spring force is its greatest here, and as it moves in, its spring force decreases, and at this point right here, our force from the spring is equal to 0. So at this point right here, our spring potential energy is 0. Right here, our spring potential energy is at its max for the way I've set up the system. Now, since we have conservation of mechanical energy because the spring force is a conservative force, at x equals 0, this was where the velocity, the kinetic energy is going to be at its max. And that means our velocity is going to be at its max. Okay? Here, where I started, my kinetic energy equals 0. As it moves through here, it's going to move out to a position minus x. Here at minus x, V is going to be 0. So the kinetic energy is going to be 0, and the spring potential energy is going to be at its max. Okay? So we can say that the mechanical energy of the system total could be calculated from the maximum displacement, 1/2 kx squared, or the maximum volume of the velocity at x equals 0, 1/2 mv squared. And at any point in between, we can always say that the mechanical energy, actually that should be E. That should be E. I'll have to go back in and fix that, guys. E mechanical total is 1/2 kx squared plus 1/2 mv squared. Let's see if I can get this fixed right now. Okay, I'll have to do that on my own computer. Close that down. So I'll have to go in and fix that on my computer. I'm not at my computer. So this should be E mechanical. Total equals 1/2 kx squared plus 1/2 mv squared. All right, guys, I gotta go give a test. So we will pick up here and we'll start looking at some problems next time I film. See you in a bit.